Hey, we're going to take a look at some things that we might help us in our work in solving some of the problems for finding derivatives of natural exponential functions and natural log functions. So just some previous knowledge. Rules for combining a natural log and a natural exponential. These are inverses of one another. So some of the things that we can do, if you end up with a result like this, okay, one thing you could do is you could move the 2 in front because we have a log property. Wanted to, and say 2 natural log of e. Okay, well, right now you might want to zip down here to the bottom. One of the things that we might want to memorize is the natural log of e and that value. I want you to think about e to the first power. Natural log of e is undoing itself, and we're back to what we started with, and in this case the exponent is what we started with, and that's 1. So that's one important value that you might want to kind of memorize. Natural log of 1 is 0. And you can really get an understanding of those values if you looked at the natural log function. Okay. If you look at a natural log function here, we know this value is 1, 0. So if you're asked what's the natural log of 1, you're asked for what the output is, and that's 0. Okay, if you look over here and consider this to be e, because remember e is a number bigger than 2 but less than 3. Okay, we're talking about if our input is e, what's our output? Well, as you can see, our output is 1. The natural log of e is 1. So these would be two good things to memorize to help you with some of the work that we're going to be doing. All right, so back up here, I could use a property. I could pull the 2 in front, and I could say this is 2 times natural log of e. Well, what's the natural log of e? Well, it's 1. And so in this case, we just have 2. Another way to look at it is this way. We're finding the natural log of the natural exponential. That's undoing these two functions here. When they're side by side, back to back, following each other immediately, our answer is going to be the input, and the input in this case is 2. So let's practice some more of these. The natural log of the square root of e. You might notice that, hey, e and natural log are not next to each other, but if I rewrote it as natural log of e to the 1/2, these two will in essence cancel each other out, and we're left with an answer of 1/2. Okay, following that pattern, we can see that these two would undo. We get -1. Natural log and natural exponential undo each other, and we're left with sine x. Okay, going the other way, exponential, natural log, they follow each other, they cancel each other out, they undo each other, we're left with 2. We do have a little more work here in this problem. Notice that the natural exponential and the natural log function are not side by side, so you'd want to rewrite it. We have, focusing our attention on this exponent, okay, we can use a log property by shifting the 3 and making it 2 cubed. So in this case, these two will undo each other. We'll be left with 2 cubed, and 2 cubed is 8. Okay, next example right here, these two will undo each other, and we're simply left with x squared plus 1. So these might be some of the things that you have to think about when attempting to solve, simplify any of the problems that we're going to be dealing with. Okay, let's look at rules of exponents, something else to consider. Okay, what can we do with these expressions here? Well, they're telling me that I'm adding two things together for my exponent on e. And I know you didn't see this property in this way in previous classes, but this is what this means. If I'm adding x plus natural log of x, that means that I can take a base of e and take each of these terms and make it the exponent of that same base. Because what you learned in the past is if you're multiplying with the same bases, you add the exponents. So same exponents or same bases, you add the exponents. You can't just simply combine these because we don't know what x is. Okay, so it's just kind of a backwards approach to the property we've always known. What can we do here? I see that I have the same base. I know there's properties of exponents that say I can, with the same base, with a quotient, subtract. So this is a different way that you could view this quotient. So if I saw this, if I needed to go back to a quotient, it would take me back to here. Let's see here. Several ways to simplify this. I see I have a negative exponent. To make a positive exponent, I can take the e to the denominator with the positive natural log of x. These two would undo each other, and I'd be simply left with 1 over x. I can tell you that most students on this one, when simplifying it, what the student will do is they will take the -1 coefficient here and make it an exponent on x. So it looks like natural log of x to the -1, just shifting it here. Okay, and that way that accomplishes canceling those and being left with x to the -1. But we know that that is actually 1 over x. The same thing I found from a different approach. Just some things that might help us with our work in simplifying some of these types of problems that we're working on lately. Okay, now at this point you might want to go back to your notebook paper because we're going to be looking at the derivative of the natural exponential function. Okay, on your own paper, let's go ahead and take a look at finding the derivatives of the natural exponential parent function and the natural exponential composite function. Okay, so we're going to start with the parent function. I'm going to bring in the derivative operator. We did see in a previous video that graphically the derivative of e to the x is itself. So easy enough. I would wish that they would ask me all day long to differentiate e to the x. That would be wonderful. Unfortunately, they're probably going to give us a composite exponential function, natural exponential function, where u is just another function of x. So what does that look like when we bring in the derivative operator? You guys may have guessed it's going to be the chain rule. All right, so when we go over here and we want to find the derivative, the outside function is not a power function. We're not using the power rule. The outside function is the natural exponential function. So in that case, the derivative is e to the u. Leave the inside alone. So the derivative of the outside function is indeed from this parent function itself, inside left alone, times the derivative with respect to x of what I left alone, which was u. Some authors are going to write it as this expression. Some will say it's times u prime. It's just a personal preference. Let's look at some examples. Consider the exponential function e raised to the -t divided by 4. If I wanted to find this derivative, I'm going to consider that the outside function is the exponential, the natural exponential. So the derivative is itself times the derivative of the inside function. Well, the inside function is the exponent here. So, and I'm going to get it ready for differentiation by pulling the 1/4 multiplier out in front. So the outside function, I have identified it as an exponential. I know the derivative will be itself, and then times the derivative of the inside function. The derivative here is going to be -1/4. Okay. At this point, I mean, you can rewrite it. You're finished with the calculus. You could rewrite it if you wanted to. I noticed this could be in the denominator of a fraction. So I could have the -1 with the 4 here, with the e here, with the t divided by 4. So just an alternate way to write it. I'm going to come over here. The derivative here, outside function, is the natural exponential. So the derivative of the outside, leave the inside alone, times the derivative of the inside function. Cosine results here. I'll just put that in parentheses just to kind of keep it straightened up, cleaned up, and I'm done. Come here. E raised to the cube root of x. So my u is my exponent on my exponential function. So I might do a little rewrite on this, getting it ready for differentiation. So this looks like e raised to the x to the 1/3 y prime outside function I've identified is not natural log, it's not a power function, it's e, leave the inside function alone, times the derivative of the inside function, the u. Well, I've rewritten it here as x to the 1/3, so it's going to be the derivative of x to the 1/3. It's easier to differentiate as opposed to in radical form. So y prime equals and this now when you identify what's going on here, this is a power function. This is the power rule. So using the power rule, it's 1/3 x to the negative 2/3. Now a little cleanup on this. I'm going to go to the right here, creating a fraction. This would be 3 in the denominator, and it would be the cube root of x squared. And in my numerator, my exponential function remains. Okay, let's look at another example. Y equals e to the natural log of 2. We want to find that derivative. Well, some of you guys have quickly already identified that as a constant number. There's no variable in here, and so the derivative of a constant is 0. But if you don't see that, then you could perhaps see this, maybe, that these two would undo each other. So that's actually just 2, and y prime of 2 is 0. Some of you guys might even jump into it further and go, well, I'm just going to use my rules, okay, that I've learned. Maybe you didn't see either one of those shortcuts. So if you go right into the derivative, okay, and notice that it's an exponential function, you're going to write down 1 over the natural log of 2 times the derivative of natural log of 2. And as a result of this, again, that's 0, and by default, that whole expression is 0. So this was a constant to begin with. The derivative of any constant is 0. So you'll eventually get there whether you identify it first or you go through all the work to get there. Okay, it's building here in a little bit of intensity. Let's find this derivative here. You might see that it would probably be best just to pull the denominator up and use the chain rule. Okay, so now I'm trying to blend a few different differentiation rules here. All right, so I think that's supposed to be a negative 2. So y prime. Okay, when I look at this, first of all, I have to identify the outside function as 3x to the negative 2. Well, that's the power rule. Bring the exponent here, negative 6, leave the inside alone, drop the exponent to negative 3. But I'm going to do the setup here and say, you know what, I still have to multiply by the derivative of what I've left alone here. All right, so I'll take care of cleaning this up in a little bit, but let me jump into the little work that I have yet to do. Okay, I'm over here. Term by term. Derivative of e to the x is itself. Nice. Okay, minus. Now the derivative of e to the negative x is again itself, e to the negative x, times the derivative of negative x, which is negative 1. So what I'm going to do, I'm going to be multiplying by negative 1 here. So if I multiply by negative 1, I might as well go over here and change this sign and make it plus. Okay, a little bit of cleanup. Negative 6 stays in the numerator. Ooh, I should have moved that over. E to the x plus e to the negative x remains in the numerator. Okay, but I'm going to bring this factor down here to make its exponent positive. Okay, and let's take a look at one more. Okay, I just added it over here, number 6. All right, we need to find this derivative. Well, hopefully you've identified the two variable factors. And as a result, since neither one of these is constant, I'm going to have to do the product rule. First factor left alone times the derivative of the second. I encourage you to show the setup. plus the second factor times the derivative of the first factor. Okay. So I've got x squared. Okay, finding this derivative, not the power rule, not the natural log rule. It's a natural exponential function. It's going to be itself times the derivative of the inside function. This is just the structure. This is just part of the answer, times -3. Plus, coming over here, this derivative is 2x. A little cleanup on the first term, -3x squared times e to the -3x. Here it's just plus 2x e to the -3x. Very possible that the author may have looked for a common factor. They do like to put things in factored form. We don't have to, but I think it's good for us to continue to practice that skill. I've identified that x e to the -3x is a common factor of both terms. And when I pull this factor out of this term, looks like I'm left with a -3x plus over here, when I take this out, it looks like I'm just left with the 2. So that's our derivative there. Okay, so just looking at derivatives of natural exponential functions and their place and how to deal with them with product rule, quotient rule, and chain rule tool 2 as well.